On November 3, 2025, NASA quietly updated their classification of 3I/ATLAS. The object speeding through our solar system at 68 kilometers per second is no longer listed as a comet. It's now designated as unclassified interstellar object pending further analysis. That change happened without a press release, without an announcement, just a silent edit in the JPL small body database. But scientists noticed. And what they're finding is forcing a complete rethink of what 3I/ATLAS actually is, because the data doesn't add up. Comets have tails of gas and dust. 3I/ATLAS barely has one. Comets brighten as they approach the sun. 3I/ATLAS stayed dim. Comets outgas water and carbon dioxide. 3I/ATLAS shows almost none. And the chemical signature, the ratio of elements in its faint coma, matches nothing we've ever seen. After months of observation by the James Webb Space Telescope, the Hubble Space Telescope, and ground-based observatories worldwide, NASA's conclusion is clear. 3I/ATLAS is not behaving like a comet. It's not behaving like an asteroid, and it's definitely not behaving like anything from our solar system. So, what is it, and why is NASA suddenly so quiet about the third interstellar visitor ever detected? When 3I/ATLAS was first detected in September 2024, astronomers assumed it was a comet. Interstellar, yes, but still a comet. A frozen ball of ice and rock from another star system, heated by our sun, releasing gas and dust as it approached perihelion. That's what happened with 2I/Borisov, the second interstellar object discovered in 2019. Borisov looked like a comet, acted like a comet, had a bright tail of gas and dust. Spectroscopy showed water vapor, carbon monoxide, and cyanide, all typical for comets. It was exotic because it came from another star, but chemically, it was familiar. 3I/ATLAS is different. Spectroscopic observations from the Very Large Telescope in Chile and the Keck Observatory in Hawaii show a carbon dioxide to water ratio of approximately 8:1. That's not just unusual, it's extreme. Most comets in our solar system have ratios close to 1, equal parts CO2 and water. Some lean slightly toward more CO2, maybe 1.5:1. Even 2I/Borisov, the interstellar comet, topped out at 1.3:1. But 8:1, water is almost absent. Carbon dioxide dominates completely. Dr. Sarah Hines at NASA's Goddard Space Flight Center called it the driest object we've ever classified as a comet. But the question researchers are asking privately is whether it should be classified as a comet at all. Water is the defining feature of comets. It's what makes them active. As they approach the sun, solar heat sublimates surface ice. Water vapor erupts. It drags dust with it. That creates the coma, the fuzzy cloud around the nucleus, and the tail. No water means no classic cometary activity. 3I/ATLAS has a coma, but it's faint, barely detectable. And it's not made of water. It's almost entirely carbon dioxide with traces of carbon monoxide and molecular nitrogen. That's more consistent with objects from the outer solar system, Pluto-like worlds, Kuiper Belt objects, not comets. Then there's the brightness problem. Comets brighten predictably as they approach the sun. The closer they get, the more ice sublimates. The more gas and dust they release, the brighter they become. It follows a power law relationship. Predictable, reliable. 3I/ATLAS didn't follow that pattern. Between August and October 2025, as it moved from 2.0 astronomical units to 1.4 astronomical units from the sun, its brightness barely changed. It stayed around magnitude 12, faint and dim, far below predictions. NASA's Jet Propulsion Laboratory ran models. If 3I/ATLAS were a normal comet, it should have brightened by at least 3 magnitudes. It should be visible in amateur telescopes by now. Instead, It's still only detectable by professional observatories. That suggests the surface isn't sublimating. It's not releasing material the way comets do. One possibility is a lag, a delay between solar heating and outgassing. But lag times are measured in days, maybe weeks, not months. 3I/ATLAS has been inside 2 astronomical units since August. If it were going to activate like a comet, it would have happened by now. The chemical signature of 3I/ATLAS is rewriting what we thought possible for interstellar objects, because it's not just the lack of water, it's what's present that's baffling scientists. High-resolution spectra from the VLT's X-Shooter instrument and the Keck Observatory's Hires spectrograph revealed something unprecedented. Atomic nickel lines, lots of them, at wavelengths of 3,414, 3,510, 3,525, and 3,592 angstroms. The nickel emission is strong, unmistakable, and completely unexpected. Nickel isn't uncommon in space. Asteroids contain nickel-iron alloys. Meteorites have nickel. But in comets, nickel is typically locked inside refractory dust grains, solid particles that don't vaporize easily. You don't see atomic nickel gas in cometary comas. It requires temperatures above 1,500 Kelvin to vaporize nickel metal. That's furnace-level heat. Not something that happens on a frozen comet surface. But 3I/ATLAS is producing atomic nickel, and it's doing it without the iron that should accompany it. Spectra show no iron lines. That's chemically bizarre. Nickel and iron form together. They alloy naturally. Finding one without the other requires a specific process. Dr. John Mayen at Queen's University Belfast proposed the most likely explanation. Nickel tetracarbonyl. It's a volatile compound, nickel carbonyl, that forms when nickel reacts with carbon monoxide in cold, carbon-rich environments. It's a gas at low temperatures, and when exposed to sunlight, it breaks down, releasing atomic nickel. Nickel tetracarbonyl is rare in space. We've detected it in some laboratory simulations of interstellar chemistry, but never in a solar system object, never in anything we've observed directly. Until now. If 3I/ATLAS is producing nickel tetracarbonyl, that tells us something profound about where it came from. It formed in an environment rich in carbon monoxide and poor in oxygen. That's consistent with certain types of protoplanetary disks, young star systems where planets are still forming. But the chemistry is exotic, not like our solar system's early conditions. Then there's the organic carbon problem. Spectroscopy shows weak absorption features around 3.4 microns in the infrared. That wavelength corresponds to CH bonds, hydrocarbons, organic molecules. In comets from our solar system, organic material is common, but it's mixed with water ice, silicate dust, and other materials. In 3I/ATLAS, the organic signature is strong relative to everything else. Dr. Alessandra Rotundi at the Open University in the UK described it as an object that's more organic than icy. Like a tarball from space, a chunk of primordial carbon-rich material, barely altered since it formed billions of years ago in another star system. This composition, high carbon, low water, nickel compounds, strong organics, doesn't match any object in our solar system. Not comets. Not asteroids, not Kuiper Belt objects. It's something else. In early October, the Hubble Space Telescope captured something that deepened the mystery. High-resolution images of 3I/ATLAS showed not a smooth, spherical nucleus, but an irregular, elongated shape. The object is approximately 850 meters long and 340 meters wide. That's a 2.5 to 1 aspect ratio. Cigar-shaped. Just like Oumuamua. Oumuamua, the first interstellar object detected in 2017, was elongated, tumbling end over end. And its strange acceleration away from the sun, faster than gravity alone could explain, sparked years of debate. Natural outgassing? A light sail? Something else? 3I/ATLAS isn't accelerating anomalously. Its trajectory matches gravitational predictions. But the shape is eerily similar, and that raises questions. Why are interstellar objects elongated? Natural objects, asteroids, and comets from our solar system are usually more spherical or irregular. Elongation like this is rare. One explanation is tidal disruption. If 3I/ATLAS passed close to another star or a massive planet during its journey through interstellar space, tidal forces could have stretched it. But the odds of that happening are low. Space is vast. Close encounters are rare. A piece broken off from a larger body. Collisions in protoplanetary disks, or during planetary formation, could shatter objects into elongated shards. 3EI/ATLAS could be debris from a violent event billions of years ago, flung out of its home system and drifting through the galaxy until it encountered our sun, one that NASA scientists are reluctant to discuss publicly. What if the shape is intentional? What if 3I/ATLAS isn't a natural object at all? The elongated shape of Oumuamua led some researchers, including Dr. Avi Loeb at Harvard, to suggest it could be artificial, a probe, a spacecraft, a relic from another civilization. The hypothesis was controversial. Most scientists dismissed it, but the lack of a clear natural explanation left the door open. Meanwhile, 3I/ATLAS continues its journey, moving outward at 68 kilometers per second. By December, it will cross Mars's orbit. By March 2026, it will be past the asteroid belt. By 2027, beyond Jupiter. And by 2030, it will fade into the darkness of interstellar space. A visitor that came, baffled us, and left. Unless we figure out what it is first. Because right now, NASA has confirmed only one thing. 3II/ATLAS is not what they thought. Not a comet. Not a simple interstellar visitor. Something else. Something that doesn't fit our understanding of how objects form, survive interstellar space, and behave when they encounter a star. The question isn't whether 3I/ATLAS is strange. The data proves that. The question is whether strange means exotic natural chemistry, or something we're not ready to accept. And NASA's silence suggests they're still trying to figure that out.